Hello, everyone. My name is Johan Comparat. I'm a postdoc at the Max Planck Institute for Extraterrestrial Physics in Garching near Munich in Germany. And in this presentation, I will walk you through results about the large-scale structures seen in the X-ray, as you can see in this beautiful background picture I have in this slide, going through simulations and observations. My talk will be split in two parts. First, a quick description of the models of the large-scale structure that we've developed, particular galaxy clusters, active galactic nuclei, and foregrounds and background. And secondly, I'll go into two results: how the stellar mass is related of galaxies is related to X-ray luminosity, and how we characterize samples that we observe, completeness, purity, and so on. So first, we have to simulate the large-scale structure in the X-ray, a set of models. We start from dark matter light cone, populated with the X-ray and the optical infrared model. Then through the 60 simulator, we create events following the eROSITA scanning strategy. And with the ESAS pipelines, the eROSITA pipelines, we detect objects, we classify objects, and so on. Then at the end of the simulations, we can create a selection function and use it in scientific pipelines. So the models that go in the simulations are, for the clusters, a generative model from observations. So we take observation from XXL, XCOP, high flux SPT, generate a big covariance matrix between mass, temperature, redshift, and emissivity. So here you see these different variables, so that with this covariance matrix, we can sample from and generate all these quantities. In projection, we obtain a log and log S shown in red down to 10 to the 13 solar mass, very small groups. That agrees very well with observations from 5,000 square degrees of spiders in red, 2 square degrees of cosmos in blue, and sub-square degree results from CDFS in orange. So we have a quite accurate prediction of the log and log S of extended X-ray emitters in the sky, and this over the full sky. The AGN model is different because we have a duty cycle. So we start from the dark matter X-ray, dark matter light cone, populated with stellar masses using average relation, typically like Beruzzi or Moster 2018. And then we populate these with accretion events by abundance matching or drawing for the specific accretion rate distribution, as in Georgiakakis 2018 or Comparat 2019. We then, by construction, have a luminosity function that looks exactly like our best knowledge of the luminosity function. Finally, the last part of the model is the foreground emission from our galaxy, which you've seen in the first slide. To do this, we simply resample from the observations after masking most of the sources. You can see that there remains on the right side quite a few very, very bright galactic sources, but these we keep. We don't want to have any large-scale structure in the background of this. So now let's go into results that we obtained with these models. So the first result is the stellar mass to X-ray luminosity relation. We use the gamma observations of the galaxy population. It's 60 square degrees of almost complete galaxy sample. In this sample, we have 35,000 central galaxies that are ranked with stellar mass and star formation rate. We have an X-ray event list of about 10 million events and about 30,000 sources. We measure around all these galaxies, central galaxies, the X-ray luminosity profile for different masking schemes. We obtain around star-forming and quiescent galaxies profiles. On the left, you see profiles of the quiescent galaxies, and on the right, profiles of the star-forming galaxies. The profiles look very different from one another. The quiescent profiles look very extended. If you compare to these small dashed lines you see on the left, on the large scale above 100 kiloparsec, they are significantly above. For the star-forming profiles, they are quite consistent with the point source profile. Now, if you try and remove AGNs, let me flip there and back. You can see a huge difference, factor of 10 on the right side for star-forming galaxies, while on the left, for the quadrant galaxies, the difference is minor, 40, 50%, and the profiles remain very extended for the quadrant galaxies, even if the agents are masked, whereas for the star-forming galaxies, they remain point-like, except for the top 3 most massive samples of galaxies. So let's dive into comparison of one set of objects about 5 × 10⁻⁻ solar mass and hosted by halos of 2 × 10⁻⁻12. So where the peak of the star formation rate occurs, where star formation is the most efficient. So these, let's say, galaxies that create all these stars in the universe. We see that on the left, when we don't apply a mask, the star forming profiles are in the center dominated by a point source profile, as we've seen, AGN dominated. In the middle, we remove the AGNs, and on the right, we compare with the Illustris and Eagle prediction, as you can see in the field colors. And there are interesting discrepancies. On small scales, the simulations over-predict the emission by a factor of 10 to almost 100 or 200. And this is likely due to the coarseness of the AGN feedback and how it feeds back energy into the gas. So here we're learning something about the simulations. On the larger scale, what's interesting is the simulations, regardless of being star forming with quiescent, predict a similar emission above 100 kiloparsec, so blue and red overlap. Whereas in the observations, we see quite a discrepancy between the two. So if we integrate all of that to 300 kiloparsec, typical radius of this 3 × 10⁻12 halo, we can create this overall relation between X-ray luminosity and stellar mass that you see on the left figure. The blue points are for the star-forming galaxies and the red points for the quadrant galaxies. You see this very nice relation appearing. If you're coming from the cluster side and used to very big, very lost halos, the expectation this should follow is this sort of straight line, solid line of visualization. So of a given mass that gives rise to temperature in a halo. And the sort of horizontal with small slope line is the prediction for the AGN. And so these two predictions we get with the large scale structure models we've done, which I showed just before. The sum of the two is the dotted line, and there is fair agreement between the data and the observations. Note that these yellow curves are not adjusted to data, it's a direct prediction of the models. There is a discrepancy at Milky Way like galaxies size, right? What is it? Is it projection effects, or is it circumgalactic medium emission that is not really modeled in this straight line here? It could be both, and it's likely a combination of both. The projection effects can amount from 20 to 40%. So bringing these points here by 40% low might get it nearer to the prediction, but still not there. So likely there is some circumgalactic medium, so galaxy component that needs to be added to these models that are already quite accurate. If we decompose this relation and look at the inner 80 kiloparsecs, so really dominated by the point source emission, you see that the AGN prediction in orange lines up very well with the star-forming galaxies. The quadrant galaxies are a bit above, hinting for maybe more hot gas in quadrant galaxies than in star-forming ones. If we look at the outer shell, something we can't really predict directly with the simulation, we see that we have upper limits for most of the star-forming galaxies, some detections of hot gas around the most massive star-forming galaxies, and then the observations from quadrant that follow previous measurements from Anderson in 2015. And here is the total relation. If we try to compare with the stress simulations, we say that on small scales, there are some difficulties in predicting the volume filling gas emission. For the quadrant galaxies, it's actually very nicely predicted. For the star forming, it's overshooting by quite a factor. At the intermediate scale, so let's say CGM scale, no galaxy scale, prediction at high mass works, but sort of breaks down at Milky Way mass, where we expect to have maybe more of a CGM contribution. And overall, well, if we sum the two, there is a fair agreement with some discrepancies to be understood on the smaller masses regime. An outlook for this project is that with ERAS, with larger samples, we'll be able to gain a factor of 20 in signal to noise in these measurements. And we will have a lot of weak lensing data to calibrate the stellar mass to Hall mass relation of these objects, so that we can get a very accurate stellar mass to X-ray mass relation that can be studied as function of azimuthal angle, AGN activity, or morphology. On top of that, we'll be able to measure X-ray spectra and disentangle possible multi-temperature components using the spectrum. The second result I want to walk you through we obtained with these simulations is a complete characterization of the samples we have at hand and we will have in the future. I'll show you results using simulations, so 18 simulations of the E-phase observations, which is 1,400 seconds time and 140 square degrees. And this is in this paper, and results from this one ERAS-1 simulation, 200 seconds typical exposure time, and an area of 17,000 square degrees, and this work is submitted with Ricardo Seb. And here we obtain that for in the EFET in the 1400 seconds simulation, for a detection likelihood of 8, so 10 cluster photon or 5 AGN photons, which is not so many, we have a spurious fraction of 2%. Look at the blue line, the single band detection, 2%, and a completeness of 72%. If you want to increase completeness, you need to decrease the detection likelihood threshold. And if you want to decrease the spurious fraction, you need to increase this threshold. Now we can look at trends. So here's the same figure, again, normalized at 10 to the minus 14.2 in flux to compute the completeness. We see that for AGNs, the detected fraction, so the sort of completeness is mainly driven by flux in the input source, and you have this nice sigmoid function. While for galaxy clusters, it's quite different. So you have a function that evolves much more slowly with flux, and this is due to the extended nature of these objects. So the first thing is the input flux, and the secondary parameters for detection are the NH, the local obscuration of the AGNs, and you can see that if it's heavily obscured at, let's say, high redshift in green, you will need a lot of luminosity to actually see it, to detect it. While if you are not much obscured, so log NH minus 21, and relatively low redshift, you will need much lower luminosity to detect your AGNs. These trends are perfectly understandable, but you have to think that in your survey, you have to integrate all of these trends into this completeness spurious fraction figure. For the clusters, the leading effects are the size of the sky. So if the clusters are bigger in red or smaller in green, and if they are at low redshift in red or higher redshift in green. So these are the leading trends in the X-ray detection of the clusters. So that's for these simulations on EFEDs, which is a small field to a great depth, 1,400 seconds. If we move to the ERAS-1 simulations, which include much more area, but to a much shallower depth, you can see that for different exposure times here given in the color scheme, for the AGNs, the completeness spurious fraction curve and the completeness contamination curve. So a spurious is just a detection related to background emission, and a contamination is a detection related to another source, but that is not dominant in the total. So this one we can classify, for example, a cluster contaminates an AGN, and so, or the opposite. And you see that here at lower exposure times, to have a similar few percent spurious fraction, you need to increase your, let's say, detection likelihood to about 10. These curves, note, they are normalized to different fluxes for the completeness, so to have a 50% or 80% completeness. For the clusters, the curves are a bit more scattered due to the small number of clusters that are on the sky. The convergence of this measure is lower, but the trends are very similar. That if you are above a detection likelihood of 20, basically, you have almost no spurious, and the contamination remains below 5%, which is excellent to do sample analysis. One of the points in the clusters is that they have an extended profile, and the profiles, they are not all the same. You have cool core clusters and non-cool core clusters. Here on the y-axis is illustrated the emissivity in the center of the cluster, 7 being very luminous, and 4 being with a, sorry, 7 being with a low luminosity in the center, and 4 with a high luminosity in the center. You can see that the intrinsic distribution of our simulated population covers well the plane. And if you ask, how many have I detected as extended in my X-ray photometry, then above fluxes of -10 to -12, there is not much trend with the emissivity in the center around, and there is a transition reading to -13, where if you are more peaked, you have a slightly higher completeness. And this is even more visible if you consider clusters detected as point source. They don't have enough photons to be an extended source, so they end up being classified as point sources. And you can see this strong gradient here that basically to detect a cluster with a flux of 10⁻14, it will need to be peaked because there will be only very, very few photons. So in summary, we have endeavored these new LX star mass relation that really validates our agent and cluster large-scale structure model. And we have hints of detection of the CGM around Milky Way analogs and interesting differences in profiles that are likely teaching us something about how to simulate agent feedback. Second result is we have characterized the samples and how to select for your science the best sample that is well suited, and investigated trends with properties. As an outlook, we'd like to study agent clustering to further complement and constrain the models, look at galaxy models, CGM of small galaxies. And yes, this work will feed into the eROS selection function and large-scale studies of clustering. Thank you very much for listening, and please contact me if you have questions on Slack or other.